We want to start. So we are going to start now the third and final session of this symposium today, which will focus on the interaction of light or electromagnetic waves with nanostructures. Our first speaker is Professor Sir John Pendry. Is also the Dan David laureate for this year. And so we don't, the common theme in this symposium is that we don't say all the prizes because then it will take a long time. But we do mention the connection with Tel Aviv. So I should say that Professor Pendry was here 1 year ago. He gave a very nice tutorial on in the winter school that we had last year in nanophotonics, and he's going to come again in next winter, right, for another winter school that we have. So it's a pleasure to have you, and now we look forward to hear your talk. So please.
Thank you very much, Adi. It's a pleasure to be back in Tel Aviv. Do I have a pointer? Because I will need one. Okay, we got that up. Okay, I'm ready to go. Right, I want to talk about how we control nanoscale light. But first, I should mention some people who are involved with that. Paloma is actually here today. She's a postdoc in our group, and she's one of the scholarship awards, and I'm going to mention some of her work. Oh, I should stay near the microphone. Yes, thank you very much. Yes, so Paloma I mentioned, and all these people have been involved with the work I'm going to talk about today. So why should we want nanometer control of light? Well, using light to see very small objects inside a living cell, and there was the Nobel Prize for this a couple of years ago. The Abbe law of diffraction limits what you could see with a conventional microscope to something a bit less than a micron, and that's just where the really interesting things inside cells begin to reveal themselves. So biologists are really desperate to have microscopes that can see beyond this limit. We conventionally make electronic circuits for laptops and iPhones using light to make those circuits, and so to some extent we're already controlling it on the nanoscale. Might want to sense single molecules. Problem here is that if light is a photon is about a micron across and a molecule is about a nanometer across, it's a conversation between a mouse and an elephant. And if you could bring the photon to crush it down to the same size as a molecule, then the probability of the photon interacting with that molecule will be much, much greater. Another issue which we might run into is to make light interact with light. So electrons interact with electrons very readily because of their charge, and through that we have extremely sophisticated control of electrical currents, which ultimately lead to all the chips inside your computers and iPhones and so on. But light doesn't naturally talk to light. This beam of laser light passes straight through all the other photons which are coming into the lecture theatre. And to make it talk to light, you need very, very high densities of photons. At the moment, that implies very high powers. But if you could take the same power and pass it through a much smaller area, you could get the same density of photons and still see the nonlinear effects. but at much lower power densities. Power, energy density are different things, of course. And then you can do tricks like switch light, but also these lovely things like time reversing light, which is, I'm just waiting for that to happen big time on the nanoscale. So I've already mentioned the Abbe limit, which says that using conventional optics, you can only focus to something a little better than half a micron. So, yeah, sorry. Today's deliberate mistake. Okay, so this is Snell's Law, which you all know. And today it's still used to design equipment. Why is that? Because we obviously have Maxwell's equations and have had them for 150 years or so. And the reason is that if you stare at Maxwell's equations, it's very hard to decide how light will move at a surface. Somebody in the audience put his hand up and said, yes, I find it obvious from Maxwell's equation. How many of you find it obvious? I wonder. I don't. And the reason we use Snell's law is that it gives us this tremendous intuitive feel of how light moves. We have a picture of light as a stream of particles, a stream of photons, which change their direction when they meet an interface. And if you want to design a lens for a camera, you can imagine how if you change the shape of the surface of the lens, then you would change the direction of the photons. So it's very intuitive, but also it misses out a huge amount of the physics, because it knows nothing about the wave nature of light. It doesn't even know that some of this light, this beam can split into two, and some of it reflect from the surface. And also, it has absolutely nothing to say about the nanoscale, because all this is predicated on the assumption that the dimensions are much greater than the wavelength of light, because if they're not, you can't define rays of light. They immediately spread out into something else. So what we must do is delve inside the structure of the photon. And when we do that, we find, as I'm sure all of you know, that light consists of electric and magnetic fields dancing around one another. And the first guy to point that out was a combination of Michael Faraday and James Clerk Maxwell, who completed the picture. And what Faraday did was to introduce a very new concept into the way we describe electricity and magnetism, and indeed all force fields. So before Faraday, people talked about forces such as gravity or electrostatic forces or magnetostatic forces. They spoke about them in terms of action at a distance, and the force acting along the line connecting the two particles which were interacting, or the two charges. But Faraday had a different way of looking at things. He introduced an intermediary, which is the field. And he said that what happens in magnetism, if you have a force between a north and south pole, is that first one of the poles creates a field. And it says that field which exerts the force upon the second pole. Now, you might think that's a sort of unnecessary decoration of the theory of magnetic force, because usually we take the simplest explanation, and it's undoubtedly action at a distance along the line separating the poles that is the simplest. This is the way Faraday thought about it, and the reality of his fields he could reveal with this experiment, which kids still do, I suppose, in which you put a piece of paper over the magnet and scatter iron filings, which then trace out the field lines. Now, that was actually, although it was a decoration of the existing theory, it was an absolutely crucial step, because the forces in electromagnetism, as opposed to the forces in magnetism, cannot be described by action along the line separating the interacting objects. You have to have another dimension which is provided by the field. And so Faraday showed that if the magnet was encircled by a coil, and there was no motion in the system, then nothing happened. But if you move the magnet, then you saw a deflection in the galvanometer because it induced an electrical current in the coil. And he showed that the EMF, the electromotive force in the coil, was proportional to the rate at which these field lines cut the copper wire. And so you have the field lines going this way, the copper wire going that way, and the motion going this way. It's essentially three-dimensional, and the field was central to the way you described that. It's a paradox, I feel, that Faraday was a man who knew no mathematics. He was a son of a poor blacksmith and self-taught, but one thing he didn't teach himself was mathematics. He was confessedly ignorant of mathematics. And yet it was this construction, the invention of field theory, which actually nearly all of modern physics is formulated in terms of field theory. And here was the guy who knew no maths and thought about it. But somebody who did know a hell of a lot of maths was James Clerk Maxwell, and he put the whole thing together. And this was his mathematical formulation, of course, as you all know. And he added this equation here, which makes the equation symmetric in electric and magnetic fields. And it's these fields which we're going to use to replace the rays of light. So instead of thinking of physical entities, of streams of particles, we're going to think of bundles of fields as the elements we manipulate, because these are the ingredients of Maxwell's equations. And if we make our formulations consistent with Maxwell's equations, then we have an intuitive picture which at the same time is exact at the classical level. So there's Maxwell, and somebody else who's part of our story is somebody who needs no introduction, Albert Einstein, and he also had a theory of fields. So Newton said that gravity was action at a distance along the line separating the two objects, sun and earth, what have you. And Einstein said, no, that what happens is a field is created, and the field is the metric, which describes how the gravitating object, in this case the sun, distorts space. So he didn't dismiss space as nothingness, it was just another material with properties. And the property he was concerned with was geometry, and he described the geometry, as many of you will know, in terms of the metric. And the metric just tells you how much space is crushed or stretched by a gravitating object. So that was his picture. And because space is curved, the planets do not move in a straight line as they would in a flat space. They move in curves. They move in orbits around the sun. And he could explain all that. But one thing that he did say was that, of course, space is curved. Then light moving through a curved space should also notice that and should also be bent. And that was very, very controversial, because Newton had said that gravity acts between two massive objects. And here, in the case of the sun, only one of the objects is massive. It's a bit like Blackadder, for those of you who know that series. Those of you who don't, it's a secret joke, but only one of them has to be massive. And that was very, very controversial and denied by many people, but was confirmed in a famous experiment in 1919, which was a sort of reconciliation designed as such between the two nations after the war, because Einstein was a pacifist, and also Arthur Stanley Eddington was a pacifist. He was a Quaker. And they were in correspondence about this theory, and Eddington, an astronomer, measured the deflection of starlight by the sun during an eclipse, because obviously you can't see the stars if there isn't an eclipse. And it was consistent with Einstein's theory, and that is one of the pillars on which Einstein's theory of general relativity is based. So we're going to take these ideas of bending space as part of our way of manipulating light. So we imagine that if we start with a field line, it could be electric or magnetic. It could also be the pointing vector, which you can say is more or less like a ray of light because it's a flow of energy. And if we want this to go in a different direction, then we can pull on space. And these field lines are embedded in space, so if you move space and stretch it and pull it, then the field lines have to move with it. So we pull a bit on this rubber space, and the field lines move, and when we get them where they want to go, that's it. Now, something else that Einstein said was that if you rewrite Maxwell's equations in the notation of general relativity, including his metric, which describes how much space is bent, then what happens is that the metric sits in the same place as would the refractive index in Maxwell's equations. And so you don't have to have a black hole or something massive close by. You can simply ask, what will be the metric of this space, and then say, oh yes, well that's okay, we can do metrics for light using the refractive index. Actually, a more precise way of saying it would be, Einstein said you can find out how to transform epsilon mu so that if you have this bent space here, then you can regard this as a coordinate transformation, and the first derivative of that transformation then tells you what values of epsilon mu at every point would send the light in this direction. Now I hear you cry, that isn't very intuitive, so I'll give you an intuitive way. There's still a formula. So let's ask what happens to the simplest distortion of space. What happens to epsilon and mu? So I'm going to crush space in this direction. And if I have a pointing vector like this, think of it as a ray of light, then the ray of light will follow a bend trajectory if you make a squashing of this middle section here. Now I could prove that to you, but I don't have enough time to do that, so let me just state the conclusions. They're very simple. If you squash space in this direction, then along the direction of squashing space, epsilon and mu are decreased by the same factor as you squash space. Of course, you've squashed it in this direction, so space is anisotropic, and in the direction perpendicular to the squashing, epsilon and mu are actually increased by the inverse of the squashing factor. So decrease, increase. And I could actually crawl over this piece of distorted space here, and I could ask myself how much it is squashed in this direction, this direction, this direction, how much it has been twisted, and I could tell you, using a ruler and a protractor, what epsilon and mu will be at every point in this space. So we have a geometrical equals, in my mind, an intuitive way of thinking about how to move rays around in a manner which is exact at the level of Maxwell's equations and therefore applies on the nanoscale. Now, I don't want to talk about invisibility today because I've talked about it far too much, but I will mention it because it is a beautiful illustration of the power of this method. So very, very briefly, to make this central object invisible, what you have to do is to guide light rays around it and then have them emerge on the other side so that they're traveling in the same straight line as they would be if there wasn't anything there. So you're allowed to deviate the lines, making them flow like water, but they've got to come out in exactly the same path as they would do if there wasn't anything there. So anybody looking here sees straight through this thing and sees what's on the far side. Now you could, if that cloak was big enough, use the laws of refraction to design that cloak. But it would be very, very hard. Think how you would do it. So you say to your grad student, we're going to build a cloak, go away and figure. So he sits down
and says, well, you know, I've got to bend this ray of light here, so I'll do something with the refractive index. Yeah, it looks good. Going around this guy here, but oops, I've forgotten where the light comes in here. Okay, so you go back, you remember that, you fix that, you make it come out in the right direction. And then you say, well, okay, that's good, but what about this other ray that comes in here? This is going to follow a different trajectory, but it's going to go through some of the other stuff which you've fixed in order this ray be right. All right, so what you have to do, it's a non-local problem because you have to remember at all times what's gone in all other places here and about all the other rays. And you could do it in a computer, but it would be a very, very hard challenge for anybody who's thought about how to compute things like that. It's a very difficult problem. Look how transformation optics would solve it. So what we do is start with an empty sphere, and we're going to make a hole in it. Space is made of rubber, so I'm going to cut a little hole here, and then I'm going to push all of space into this annulus here. I'm going to crush it. And then you could use my formula to say that space has been squashed in this direction and stretched in the other direction, and you could find what the very simple formula for what epsilon and mu must be at every point here. And as you do this, then the rule is that any pointing vectors or rays of light, any field lines will be pushed into this area here, and they cannot enter this region here because everything has been shoved out. So this is hidden, can't see in there. But the really difficult thing of not casting this shadow, of not disturbing the lines here, that is automatically achieved. If you move space, you move the rays with the space. If you don't move space, you don't move the rays. So a very, very simple answer to a problem which, if we approach it in the wrong way, would be extremely complex and difficult to solve. So when you do that, you designed a cloak. And what's more, the laws for cloaking work not only for rays of light, a pointing vector, but they've also been demonstrated to work for static magnetic fields. There was an experiment about 5 years ago which showed that. So the formula seems to work, and now what I want to do is to get on to nanotechnology and see how we would use this in nanotechnology. Well, the challenge I set early on was to bring light to a very, very fine focus, to crush light into something which is of the order of a square nanometer or less. And I'm going to use surface plasmons to do that. And just to say to those who are not familiar with this area, metals such as copper, gold, silver, the electrons are free to move inside them and behave like a sea. And on the surface of this sea are waves, charge density waves, which we call surface plasmons, and they propagate along the surface, and they can have very, very short wavelengths, wavelengths down to something of the order of the spacing between the electrons in the metal, which is about an atomic radius, of course. So very, very short wavelengths, and so these things can focus the energy they contain very closely, and they can couple to light. So if you have a dipole here and this waveguide type of structure, then this dipole in an excited state can give up its energy and excite these surface waves, which then propagate off to infinity. So this is the standard mother system which we start with. But the problem is that, of course, the light is not going anywhere you want it to. It's going off to infinity here. So we're going to do this space stretching exercise, and it's easy. We can do this in 1, 2, or 3 dimensions, but since I'm going to be drawing stuff, I'm going to do it in 2 dimensions. And in 2 dimensions, there are very neat transformations called conformal transformations which you can use. So Z is x plus iy, as we all know, and what I'm going to do is an inversion, a coordinate transformation. And this inversion has the property that it takes points at the origin, which I take at the center of the dipole to infinity, and it takes points at infinity to the origin. And points in between map into something else. So this waveguide structure, a plane maps into a cylinder, and depending on the distance of the origin from these planes, the cylinders have different radii. The dipole itself is two very large charges close together. If you map it, it's two very large charges far apart, and that produces a uniform electric field, which could in fact be due to an incident wave. And so, yes, and so these points at infinity map to the origin, which is here. So what it boils down to is that this system is entirely equivalent. Once you've solved this system, you know what's going to happen here. An external electric field is harvested at this point here and travels not to infinity, but to the origin, which was infinity. And there it is very heavily concentrated. Here's another mapping. Sorry, I had hoped to have another slide there. Okay, so what happens when you concentrate the light here is that these waves travel round, and as they travel, they go slower and slower. And it's like cars on the expressway. So if they go slower, they come closer together. So the energy density, the wavelength decreases, but also the energy density goes up. And if it were not for losses, then the energy would be infinity here. There are losses, but in fact the energy is not, the energy densities you achieve are very high, as I'll show you later. But another thing I'd want to point out about these structures, actually I don't have time, so I'm not going to do that. Now, it's been known for a long time, empirically, that surfaces which are rough and have singularities in them, sharp points or curved surfaces which touch one another, they are magnets for incident electromagnetic waves, and they do concentrate the energy very intensely there by many orders of magnitude. But it wasn't understood before this way of looking at things that they pretty much all have a common origin. So we start with the waveguide structure always, which I've explained carries waves off to infinity. And by picking the right transformation, you can transform this into, you've seen the two spheres, cylinders already. We can do two spheres as well, or a crescent, or these structures here, depending how you choose the parameters. And this one I like very much. So a periodic array of waveguides actually transforms into a knife edge. And all these structures have, all these structures here are actually related to this mother structure here and have a common origin. And by the way, the translational symmetry of the waveguide gives you a Bloch's theorem. It enables you to calculate everything analytically and to classify the states into Bloch states. And even though these states appear to not have any symmetry, they actually have a mother system which has lots of symmetry. So here are some pictures made quite a while ago in which we show light being harvested to these points here. And you can see the change in wavelength as the light goes into this point here. And actually things go off scale, but there's a very, very high density here. It's easier to see this effect as in case of here we have a crescent. And what I'm going to do is to plot the field intensity as a function of this angle here. So it's around 180 degrees that we're going to see these enhancements. So here's the field intensity divided by the incident field intensity. Note the scale. And so as you come, as the waves are excited and then come into the harvesting point, the wavelength decreases, but again, this motorway effect, you are crushing the light and achieving very high field densities. The energy density is the square of that, so that's 1 million in the energy density, and the response to things like Raman signals are that squared. So you can quite see how you get surface enhanced Raman scattering from these sort of effects. Very, very powerful concentrators of energy. Here's a plot of what happens if you bring two cylinders together. When they're far apart, there's just the single dipole resonance of the cylinder, but as you bring them together, the modes spread out, and eventually they merge into a continuum. This is a very interesting system mathematically, because when two cylinders touch, they're a finite object, but they have a continuous spectrum. Finite objects usually have a discrete spectrum, but if there are singularities in them which can be mapped to an infinity, then the spectrum is continuous. It's a curious mathematical point. Okay, so those are finite objects. You can now think of other transformations. Here's one which makes a real mess of a good old Cartesian mesh. And what we're going to do is to choose two of these surfaces of the surface of a grating. Now this isn't a grating because these are flat surfaces, but you can, for which you can calculate the spectrum. So I'm going to use two of these surfaces to bound a slab of material. And they map into this structure here, and you can see that after the mapping, you do have a grating because this surface is curved periodically. And that has been exploited. This is some work by Paloma, whose name I mentioned earlier, and who you'll have a chance to see later this afternoon. And she thought about realizing this in graphene. And the great thing about graphene is that you can model this grating by simply altering the doping, which you do by putting DC electrostatic biasing outside. And if it's not DC, you can actually make this dynamic. So it's a really fun system to play with. But just let me show you some of the simple results we have. So if you make that grating, you can calculate from how a flat surface, the modes of a flat surface, you can then calculate the modes of this grating. They're the same. And here are the absorption cross-section of a graphene grating doped in that manner. The electron density in graphene is rather low, and so the frequency of the waves is in the terahertz radiation, so it's about hundredth of an eV. And remarkably, by doping the graphene in this grating manner, you can absorb almost all the light which falls on the grating at certain frequencies. So something 1 atom thick can actually grab nearly all the light that falls on it, and you can switch it on and off at gigahertz frequencies. So that's quite spectacular, I think. What else? Yes, so this is a similar calculation where the grating is the graphene grating is replaced by silver, and here we see the grating between these two lines here, and we can calculate analytically what the profile is of the plasmon excitant. And you can see that what happens is that as the plasmon goes along the grating, it actually has to duck inside here, and so again it gets compressed, and you get a high density of radiation there. What else can we do with transformation optics? Well, years ago I was interested, and this is how I got interested in plasmonics, in electron energy loss. This is a really, really old paper, and what we calculated at that time was the energy loss by an electron traveling parallel to a flat surface, and the surface waves, the plasmons in the metal, travel rather slowly, and the electron, if it has 20 keV, travels rather quickly, so it creates a sort of plasmonic boom, if you like, and it sends out lots of surface plasmons, and that's a dominant electron energy loss when an electron goes near to a surface. So, but you might want to look at a more complex situation, which is this one here. So we have our fast electron again, but now instead of a flat surface, we've got two cylinders that it's passing by. And we can now treat this using transformation optics, because the electron has a simple trajectory. It goes so fast that losing an EV2 doesn't alter the trajectory. And so you can very simply calculate what the fields are that this electron creates. But the modes that it's exciting here are complex, and that to do this calculation all in this frame is very difficult. So you don't. You do an inversion, and then that takes these two kissing cylinders back into this flat plane here. Now the electron has a messy trajectory here, but that doesn't matter because you've already calculated its potential in this frame, and it transforms into this frame here. And all you have to ask is how these the simple modes of this waveguide respond to the excitation which the electron is giving to it, and that calculation you can do, done by Yu Liu, who's now a professor in Singapore. And here is the spectrum. There is the surface plasmon of a flat surface, and the modes which hybridize symmetrically and antisymmetrically. And here's the dipole mode of the system at the lowest frequencies. And these are different electron velocities. The beauty about electron excitation is that the selection rules are far less severe than they are for light, so you excite far more modes. And so you can get an understanding of these systems in this way. Now, the last time I tried this, well, it doesn't even show. I have a movie here. Whoa, sorry. Yeah. Sorry, the movie doesn't even show, so I won't show it. But I want to finish with, these are practical things about how we can understand how plasmons are excited at surfaces, how we can draw light down to the nanoscale and make its density thousands, millions of times higher than it would be otherwise. But I want to go back to Einstein and show that this way of looking at things can explain something else that I was involved with, and show that it's not as trivial as you might think of at first. So this is an idea which Veselago had many years ago. So here's refraction a la Snells Law, and here is a different sort of refraction which Veselago said should be possible. And if you define this as a positive angle, then clearly this is a negative angle, and according to Snell's law, this should imply that this medium here is a negative refractive index. And it was through the use of metamaterials that this was realized long after Veselago's paper. But I want to give you another take on that, because another thing which Veselago said was that you could make a lens out of this. And you can see that if you have these parameters here, so that these angles are equal, then you focus the light back to the axis, and you do so twice. But what Veselago didn't realize was that this lens could be perfect. And in fact, if you perfectly realize these parameters, it is perfect. And that's something I pointed out a long time ago. But there's a different way of looking at this, which can show that it's perfect. So I'm going to use my, I have to stay near the microphone. I'm going to use my trick of squashing space to make a negative refractive index, okay? So I take some space and I do the squashing. And as I've told you, the epsilon and mu, which are perpendicular to the squashing, increase. So the more you squash, the bigger they are. And as you squash very, very hard, infinitely hard, then epsilon mu go up to infinity. Now you all know what happens to things that go up to infinity. They come back at minus infinity. Think of 1 upon x, all right? it goes through plus infinity, then minus infinity. And it's exactly the same with these things here. So I squash a bit more, and these things then go to negative values because I've gone through infinite squashing to negative squashing, and I made some negative space. But look what's happened in the way. So we made something with a negative refractive index by squashing. But what's happened to space? It's something really crazy. Okay, so this space, it was squashed. You can sort of understand that. But what about this space? Huh? It's got 3 manifolds. It's triple valued. And so what the light does is if it comes to a focus here, and it goes around the corner, it comes to a second focus because it retraces its steps, and then when it comes to the second edge, it goes back again to where it came from, and so what you think is happening is that light's going through here, but what the light thinks it's doing, because it sees this as a metric of the space, is that it thinks it's going around here. So it actually sees a focus 3 times. Now that's a statement which is not made depending on the ray approximation. It's a statement which depends on Maxwell's equations. And so, according to Maxwell's equations, this focus, if it's perfect here, or if this is the origin of the light, then the focus should be perfect here and perfect here as well, with providing you realize all the parameters. And so that's one way of looking at negative refractive index. So it's time for me to finish. In practice, I've probably gone over time, actually, sorry. What I hope to have shown you is that this way of transformation optics, of looking at optics on the nanoscale, is a very powerful tool. It's an aid to your imagination as much as a way of calculating things, and also it reveals to us some very profound things about the geometry of optics. I challenge a cosmologist to give you an example in the cosmos of negative space, but we can do that with optics. And then just to conclude, since I'm over time, I will leave you to read the conclusions. Thank you very much for your attention.
Thank you very much for this excellent talk. So, are there any questions? Yes, please.
If what do we learn from this from the perspective of stealth technology?
You're taking me back to invisibility. Well, you learn that you can hide something and people have built. You learn that you can hide something and people have built cloaks, yes?
The fact that I can hide something is obvious. How do I hide it in practical terms?
You build a material which does this job of yeah, it depends on the material. And I use, or experimentalists use things called metamaterials to realize the structure of that cloak.
And the criteria for the material, if you can summarize 3 short characteristics.
You apply my formula to the crushing argument, and you get a material which has a large epsilon in this direction and a small one in this direction. Same from you. It's a very simple formula. David.
I want to go back to Maxwell. You know, if Maxwell realized that his equations do not always have a solution.
He didn't tell me if he did.
Well, I'm asking, is it known?
It's not known to me, no. Do you know it?
No, that's why I asked the question. You know the answer. I mean, you know the answer that it doesn't always have a solution. I was wondering whether Maxwell, being such a great mathematical physicist, might know familiar.
Well, I do know that he fretted very, very much about his equations, and in those, you see, up to about the time of Maxwell, people described things in terms of light is something that moves in rays. It was very, very pictorial. And these days, certainly in physics, you're not content with a subject until you have an equation which describes it. But that really started about Maxwell's time. And he was very worried that his equations were not just mere equations that describe reality. And he constructed all sorts of models with rollers interlocking in space like gears to try and show that his model, his equations really did describe reality. Yeah.
Okay, last question, Amir.
All losses are usually inherent. Well, what happens
With the perfect?
perfect lens when you have losses?
Yes.
Small losses.
Okay. So that's a very insightful question. It ruins it. And the reason is that the way what you have to do in the perfect lens is, I didn't describe it in detail, is that you have to take those waves which are localized near the surface and decaying exponentially, and you've got to boost them back to the level that they were where they started from. And the way you do that is using resonances to amplify the signal. Resonances are devices which can gather energy on the fly and can build up very, very high amplitudes without having a power source within them. But the finesse of a resonance is limited by losses, and so the resolution of a perfect lens is not an aperture limited resolution. It's limited by the degree to which you can build perfect resonances, and that's a question of loss, I'm afraid.